We're going to do 2 more series tests and then try to put them together for Monday. The first one is called the direct comparison test. Of the 2 tests, I think direct comparison is a little bit harder to think about because you have to plug in numbers and figure out which one is bigger or greater. The second test that we'll do, I think that's a little more straightforward. This one, sometimes they abbreviate it with DCT. So if I say DCT or direct comparison test, you'll know which one we're talking about. So with both of the tests today, direct comparison and limit comparison, that's the second one, you have to pick a function that looks similar to the function that you're talking about. And for direct comparison, there's 2 rules, okay? The function that you're given is a of n, and the function that we're going to create is b of n, okay? So a of n is the given one, b of n is the one we're going to make, okay? If you pick a function where b of n converges, and then you find out that b of n is greater than a of n, then that means a of n will also converge. Because if b of n is greater and it converges to some sum, then anything less also has to converge to that much or less. It can't be bigger, so it can't diverge. The second one says, well, let's let bn diverge. Well, if you find out that bn is less than an, if bn diverges, an also has to diverge. Because if bn is less than an is bigger, if bn is already getting to be infinity, an is also going to be infinity. So these 2 rules you sort of have to memorize and you got to think about and make sure that you understand why each one is the same. So let's look at some examples. Let's say that we have 1 over 3 plus 2 to the n. Alright, and we're going from 1 to infinity. So first thing you have to do is you have to pick bn. And a lot of times it's easy just to pick something that the function looks like. For example, 1 over 2 to the n. You just sort of get rid of some numbers and make it look sort of the same. Alright, now what do we know here? Well, on the bottom we have 3 plus 2n. So that means that the bottom of this fraction is bigger than 2 to the n because we're adding 3 to it. Well, if 1 over something that is bigger is compared to 1 over something that is smaller, what does that mean about the function? Well, since the bottom is bigger on the left, that means the fraction itself is smaller. So I know that this function is smaller than this function. Now, what do I know about this one over here? Well, that is a geometric series where r is a half. This is the same as saying 1/2 to the n. Both of those are the same. What that means is that this function converges since it's a geometric series. Alright, so the bigger function converges. If the bigger one converges, that means the smaller one also has to converge, and that's called the direct comparison test. So you pick a function, you decide if it converges or diverges, and you see if it is bigger or smaller than the one you started with. Okay, let's look at another one. So let's look at 1 over 5 to the n plus 1. Well, it looks like maybe we would pick, I don't know, 1 over 5 to the n compare it to? I know that this one converges because, again, it's geometric where r is a fifth. Alright, the fraction itself is smaller. Since the bottom is bigger and it's the same on top, that means the fraction itself is smaller. So we have a converging series that is bigger than the other series. That means that this one has to converge by the direct comparison test. Sometimes it's hard to figure out what's going on. So let me give you an example. If I had this one, I would probably try to compare it to 1 over square root of n. And what you'll find out is that this one is smaller than that one because the bottom is bigger, so that makes the fraction smaller. Well, I know that this diverges by the p series, where p is a half, because that's the end of the 1/2. Well, if you have a diverging series, and the function we're looking at, or series we're looking at, is smaller, we don't know what's going on with this. So what that means is this is not the way that we're going to solve this problem. So we have to pick something else. Well, when something like that doesn't work, pick something similar maybe. Let's get rid of the square root. We know that this diverges by p series. We're hoping to find out that this one is smaller than the other one. And if you start plugging numbers in the calculator, if you plug in a 1 for n and compare them, if you plug a 2 in for n, it doesn't appear that it's going to help you, but if you start with 7 or 8, it actually, you can see a pattern. So I'm going to start with n equals 8, and I'm going to plug it into both functions. So the first one is 0.146, and the second one's 0.125. And I find out that the 0.146 is bigger. Let's go ahead and plug in n equals 9. I get 0.143 and 0.111. What I find out is that as n is larger, plugging in 8 or 9, that this function, the 1 over n, is less than the previous one we started with. Since it's a diverging series and it's less, that means that this original series diverges by the direct comparison test. If you have trouble trying to decide which one's bigger and which one's greater, you can plug in n equals, and I would start with 8. And I don't know where the number comes from, but I know that if you start with 8, it'll work. If you have trouble and you can see a pattern after n equals 8, maybe plug in 8 and 9, maybe 10, just to make sure. That might be something you would have to do to find what you're looking for. Now, for the limit comparison test, I think it's a little bit easier because you don't have to try to guess as much. You still have to pick a function, but as far as working the process out, it's a little bit easier. So what it says is an is the function that you pick, or that's given, and bn, again, is the one you pick. So what it says is that if you find the limit as n approaches infinity of the one given over the one you pick, if you get a limit, meaning you get a number, then the two series behave the same way. Meaning they both converge or they both diverge. So if you pick something that diverges and you get a limit when you divide them, then the answer is diverging. If you pick something that it converges and when you divide them you get a limit, that means that they both converge. Okay? So let's look at some examples. Let me go back here and see what number we're on. This was number 3, so we're on number 4. Okay, let's say that I have this one. Well, I think I'm going to compare it to 1 over n. So I'm going to find the limit as n approaches infinity of 1 over 2n plus 3 over 1 over n. Alright, simplify, like 1 over 2n plus 3 times n over 1, so I get n over 2n plus 3. Alright, if I find the limit, I get a half. Alright, I got a limit. I got a L. Let's go back. This one diverges by the p series because p is 1. So that means the original series diverges by the limit comparison test. So you take the function that you're given, divide it by the one you pick, find the limit, see if you get an L. You can't get infinity, you have to get an L. And then they both behave the same way. Okay, let's pick another one. What do you think we'll compare this to? Oh, we'll get rid of your numbers, maybe 1 over n squared. Which I know converges since p is 2. A lot of times you're going to pick a p series or a geometric series to compare it to. So the limit is n approaches infinity of 1 over the one we started with over the one we pick. Simplify, 1 over that times n squared over it, so we'd have n squared over this. Alright, that limit is 1/3. I got a limit. We're good. That means that these behave the same way, so the original one converges by the limit comparison. Maybe I'm going to compare this to 1 over square root of n. So the limit as n approaches infinity of that over that. Cross multiply, simplify, you get this. Same power on top and bottom, so we can simplify, take the square root of 4, we get a half. That means they behave the same way because we got a L. This diverges since p is a half. So that means the original one diverges by the limit comparison. So you get a number. These two things behave the same way. Alright, one more. This one's kind of strange. And not very often, but sometimes you're going to have to pick something a little different. Okay? Oh, this is 2 to the n, I'm sorry. So I just want to show you this one, although not very often you won't have to pick something like this. I'm going to compare it to 2 to the n over n squared. I'm coming up with n squared because there's an n and an n cubed, and if you got rid of them, that would be an n squared. Now, again, not very often this will happen, but I just want to show it to you anyway. If you did L'Hopital's rule here, and then continue to do it, you're going to end up with the number on the bottom. So this is going to approach infinity, which means that one diverges. Alright, so that's why I'm going to compare it to that. So I'm going to divide that. I'm going to take that and divide it by that. So I'm going to skip a step. Instead of dividing, I'm going to change it to times and go ahead and flip it. So 2 to n's will go away. Now I have n to the third over n to the third, so I get 1/4. I got a limit, so that means the original one diverges by the limit comparison. I want to tell you, just for the sake of some of the problems we're going to be looking at, if you end up with something like 4 to the n over 4 to the n plus 3, and we want to find the limit of this, I will tell you, because the powers are the same and everything, this limit will come out to be 1. It's kind of like using the asymptote rules, but it's something to a power, so that changes a little bit. Just wanted to let you know, you could do L'Hopital's rules on that to prove it, but it does come out to be 1, so you would get a limit on something like that. Alright, here's your try problems. On the first one, I want you to do direct comparison test. And then on 2 and 3, both of them, do limit comparison test. And those are all n equals 1 to infinity, but for the process here, you don't really have to solve that out.